Hi, everybody. This is a quick lesson about how to draw Lewis structures for molecular compounds, and then we are also going to draw Lewis structures for polyatomic ions. Near the end of the lesson, we will also show you how some ions and molecules have something called resonance structures. We'll try to give you some examples of that. So have a place in your notes where you can do some examples with me so that you have some examples to look back later. So the Lewis structures, when we draw them, we are going to have to figure out how many valence electrons are available to use in the Lewis structure, because it's the valence electrons that are participating in chemical bonds. And remember, all of the elements would like to get 8 valence electrons around them, except hydrogen, which only needs 2 because level 1 is full when that S sublevel is full. When we draw the Lewis structures, the bonds are going to be shown using lines. Each line represents 2 of the valence electrons. And then unbonded electrons are going to be shown as dots, and each dot is 1 electron. So we're going to do a lot of drawing here. And we're going to start with a compound called methyl bromide. Okay. Now, the first step is to figure out how many valence electrons you're going to have available to use in your structure. Okay. So I'm going to go through, so carbon, we have 1 in the formula. Each carbon has 4 valence electrons. Remember, you can get that by looking on which column it is in the main block on the periodic table. And so that means that there's 4 valence electrons available from carbon. There are 3 hydrogens in this structure. Each hydrogen is going to bring 1 valence electron to the structure. So the hydrogen will contribute 3. And there is 1 bromine. Bromine is a halogen, and remember, in the main block, they all have 7 valence electrons. So since there's only 1 of them, that contributes 7. And this is an important number to know. This is the number of valence electrons that are available to use in this structure. Okay, so we're going to have to remember that number. The second step is that you draw a skeleton structure for your molecule. Now, you want to put the element in the middle that is capable of making the most bonds. I always tell people, put the neediest element in the middle. Remember, carbon needs 4 more electrons to fill its valence shell. Hydrogen only needs 1 more, already has 1 and only needs 2. Bromine already has 7. It only needs 1 more. So who's the neediest? Carbon. Okay. The other thing to remember is that the halogens, remember, bromine's a halogen, and hydrogen, they can only ever make 1 bond, so they are never going to be in the middle. If you've got carbon or nitrogen in the structure, put them in the middle. Even oxygen is in the middle, sometimes with molecules. But the halogens and the hydrogen, they're never going to be in the middle. So when it says to draw a skeleton structure, you're drawing bonds. So we know that the carbon has to bond to 3 separate hydrogens, and we know that it has to bond to a bromine. Okay, this is what our skeleton structure will look like. Okay, so I'm going to transfer that to the next page. So I've got carbon, and does it matter which side you put hydrogen on and which side bromine? No, just as long as carbon is in the middle, and there are 4 sides to carbon, and there's 4 elements. So a hydrogen on 3 sides, and then a bromine on 1 side. So remember that we had 14 valence electrons available. What you need to do is subtract out the valence electrons that were used in making the bond. Remember, each one of those dashes represents 2 electrons, and I have 4 dashes in my skeleton structure. So I used 8 electrons to make those bonds. I have 6 that remain. Okay, so that is the third step that you do. So again, here is our skeleton structure. Now, after this, I'm not going to keep redrawing these because I'm going to just do it on one slide. But remember that we started with 14 valence electrons. We subtracted out the 8 that we used in those 4 dashes. and we had 6 that remained. Okay. Now you look at this, carbon doesn't need any more electrons. It has 8 around it already, 2 from each dash. Hydrogens only need 2 electrons. They each have a dash, so they're all full. And we can look at our structure and we see that right here, bromine would like 2 more. Here, bromine needs 2 more. Here, it needs 2 more. It has 2 with the dash, but then it needs 6 more. Well, we have 6. That's perfect. So we know, oops, thought it was going to the eraser. We know exactly where those electrons need to go, okay? And we can go back and put those into our picture. And this is what the Lewis structure for methyl bromide would look like. So what we're going to do in this presentation is just take those 4 steps and continue to do it for a number of different variations on different types of molecules, just so that you have a lot of experience. And then we'll give you some just to do on your own this evening. So there's the 4 steps, okay? And the new molecule that we have up there is formaldehyde, okay? CH2O. So let me get a pen. Okay, so carbon, there's only one of them, so it's going to have 4. My screen isn't writing as well today. Hydrogen, there's 2 of them, and they each have 1, so that contributes 2. I'm abbreviating, from my previous one. I'm not writing out the steps as much. I'm just totaling up. And I have 1 oxygen, which has 6 valence electrons. So I have a total of 12 valence electrons that are available to me. Okay, so let's draw the skeletal structure. That is step 2. I'm going to put carbon in the middle, and then we've got 2 hydrogens and we have an oxygen. Okay, now one of the things that I need to do, right before I do number 4, number 3, subtract out the electrons that are used in the bonds. I used 6, so I have 6 that remain. I can put 6 dots on this picture. And one of the things that's very helpful is to kind of figure out, well, how many dots would I need to complete all the valence shells? Now, the hydrogens don't need any. Carbon would like 2 more right here. Oxygen would like 2, 2, 2. Do you see how I actually need 8 electrons to finish out my picture, and all of the elements, have a full octet? So I've got a discrepancy right here. I need 8, but I only have 6. Anytime you have a discrepancy, that means that you're going to have multiple bonds in your structure, meaning like a double or a triple bond. So, for example, I know hydrogen cannot make any more bonds. Their outer shell is full. So I'm going to figure that that double bond is between the carbon and the oxygen. Now, carbon's valence shell is full. It's got 1, 2 electrons here, 2 here, and then 4 here, 2, 2, and 4. That's a total of 8. All the hydrogens are full. Okay, now I need to subtract out the extra 2 that I used. So remember, I was at 6, right? Okay, so I had 6. I used 2 more, making the double. I have 4 electrons left. Perfect. Oxygen needs 4 more electrons to have a full valence shell. This is what the structure of formaldehyde would look like. So let's do another one. Here's nitrogen, like the gas that's in the air. All right, so I have 2 nitrogens. Remember that they each have 5 valence electrons, so I have 10 available. Gee, the skeleton's pretty easy. We just have 2 elements. They have to be bonded to each other, right? So we put a dash in there. Subtract out the 2, I have 8 left. Let's take a look at this structure. For each nitrogen to have 8 valence electrons, I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my gosh, I need 12 more. I definitely have a discrepancy there. In fact, my discrepancy there is 4. That means that I'm going to have more than 1 multiple bond. I'm going to need several multiple bonds, okay? So if I have 4, think about that. I'm going to add 2 more bonds, 1, 2, okay? So instead of 8, now I got to subtract out those other 2 bonds that I added, and I only have 4 more electrons. Well, that's okay because each nitrogen atom now has 6 in the outer shell. Those 3 bonds each represent 2 electrons. That's a total of 6. And remember, both atoms are sharing them, so they each think they have 6. So they each only need 2 more. So I just had to put, I'm having trouble making dots over here. I just had to put 4 more dots, and there we go. That's my Lewis structure. So, think about it. Obviously molecules can get bigger and more complicated. But since we are just learning this, we will try to stick with ones that have like smaller numbers of atoms. But it's pretty much how, you come up with the structure for every atom. When you check it at the end, you want to look at them and say, does every element have 8 valence electrons? Or back here, does the carbon have 8? Yes. Does the oxygen have 8? Yes. Do each of the hydrogens have 2? Yes. And if you can answer yes to all those questions, you know that you have a viable structure for that particular molecule. Okay. Now, here is a polyatomic ion. And polyatomic ions, while they are ionic in their reactions with metals, within the polyatomic ion, it's covalent bonds that are holding the chlorine and the oxygen together in this case, or like if you have sulfate, that's holding the sulfur and the oxygen together. Those are covalent bonds, okay? The only thing you have to do differently here is when you're determining the total number of valence electrons, you have to add in an extra electron for the negative charge, okay? So for example, here we know chlorine, can't get it to right. All right, hold on. So we know chlorine has 7 valence electrons. Oxygen has 6. And then I got to add in that one extra. I have a total of 14 electrons. Now, if you're wondering, where did that one extra electron come from? Like, for example, if sodium's nearby, it's, remember, happy to lose that valence electron. Anytime an anion is made, a cation had to be made somewhere else. So that extra electron came from a metal that wanted to lose that electron. Now, again, we only have 2 elements here, so the skeleton structure is pretty easy to draw. We subtract out those 2, and we've got 12, okay? If I look at this, oxygen needs 6 more, chlorine needs 6 more, 6 and 6, that equals 12. I'm good. I can put those 12 dots around the chlorine and the oxygen, okay? And then when you have a polyatomic ion, it is proper to put it in brackets and show the charge on the outside of the brackets, because that represents the fact that there's a charge on this particular structure. If there are no brackets around a structure, then we assume that it is neutral, like the nitrogen that we did in the previous, in the previous slide. Okay. So I'll just show you another one here. Like, here's phosphate. Okay. And so the phosphorus has 5 valence electrons. Each oxygen has 6, but there's 4 of them, 4 oxygens. So that's 24. We're going to have a lot of dots to add. And then there's the 3 extra, okay, for a total of 32. Now, we have to draw our structure, and you look at this, and the neediest element in this case, the one that can make the most bonds, phosphorus needs to make 3 bonds, and oxygen only needs to make 2. So we're going to put phosphorus in the middle, and we have phosphorus here bonded to 3 oxygens. And then you think, well, what am I going to do with that other oxygen? Now, a lot of times people are like, oh, okay, oxygen can make another bond. We'll just put it on there. And this is not going to work out. And it's not what they see. There's once you get into college and maybe even in AP Chem a little bit, and you study spectroscopy, when they examine phosphate ions using spectroscopy, they do not see any evidence of oxygen-oxygen bonds. They see 4 phosphorus-oxygen bonds that are all equal to one another. And so it doesn't do this. And you say, well, then where does it do? Because phosphorus can only form 4 bonds. So phosphorus is really going to have that pair of electrons on the top. Remember, if we put those 5 dots around the phosphorus, we would have the first 2 are in the S and then the single, single, single. So it's got that pair of dots up there on the top, okay? Well, there is something in covalent bonding called a coordinate covalent bond, where the same element gave both of the electrons that are in the pair that gets shared. Usually, in most cases, each element gives one and they share. But in this case, oxygen, which has a much higher electronegativity than the phosphorus, is going to force the phosphorus to share both of those, okay? And that pair creates a 4th bond around the phosphorus. So we can replace that pair of dots with a bond, and it's a coordinate covalent bond. So once we have this, we have to subtract out the 8 that we have used. And that means that we have 24 left. 24 is the same as 12 pairs. So if you look, we have 4 oxygen. They each need 3 more pairs. There's our 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. There's our 24 electrons, the 12 pairs. Remember that since this is an ion, to complete our structure, we need brackets with a -3. Now, do any of the ions ever form like double bonds or triple bonds? Sure. There are double and triple bonds within the ions, okay? And this one, carbonate, it's going to be necessary. Let's go through this. So carbon has 4 valence electrons. I have 3 oxygens, 6 each, so that's 18. Then I got the extra 2, so I have 24, okay? So I draw my basic structure. And I have something that looks like this, right? Now, I can subtract those 6 out, and that gives me 18. But look at my structure. I need more than 18. I need 2, 4, 6, 8, 10, 12, 14, 16, 18. The carbon needs 2 more. I need 20. What do we do if we need more than we have? We make a double bond, right? So here's the issue. You say, well, where should I make the double bond? I can make the double bonds between, carbon and the oxygen that's to the left. I can make it between the carbon and the oxygen that's on the right. Or I can make it between the carbon and the oxygen that's on the bottom. And it's really interesting, but when they look at this with spectroscopy, like let's say you put it right here. When they look at spectroscopy, they can not only tell what kind of elements are bonded, they can tell whether it's a single, a double, or a triple bond. And they don't see 1 carbon-oxygen double and 2 carbon-oxygen singles. They see 3 equal bonds that are all about 1 1/3 strength, okay? And so what they think is that this double bond kind of can shift around its location. Sometimes it's the one on the left, sometimes the one on the right, sometimes the one on the bottom. And what they do is they draw something, and we're going to go to the next slide, called a resonance structure, okay? Like they draw it in all the possible places that it could be. Like the double could be to the left. The double could be underneath, right? Or the double could have been on the right. These 3 structures, once we got to put the other dots on, are all one in the same. And they feel that, and then all the evidence points to, that in reality, carbonate is really a blend of these three structures where that extra set of electrons constantly moves around its location. And so they call these resonance structures. And usually when they do them, they draw all of the possibilities like this. And then they put arrows to show that it can kind of be a blend or move around among all of the possibilities. Now let's go back. We have to put our extra dots in. So once we added that extra bond, right? We have to take that out. We have 16 left, 16 dots to distribute. So I'm going to do it right here on this one, and then I'll go add it to the other ones. So we'd have 1, 2, 3, 4, 5, 6. The oxygen that's down also needs 6. 1, 2, 3, 4, 5, 6. Do you see that the oxygen on the side, it already has 2 bonds, so it has 4 electrons. This one only needs 4 more. 1, 2, 3, 4. And the carbon doesn't need any because it has 4 bonds times 2 electrons each. So that's a total of 8. So this is one of the possible resonance structures. And you can see that the oxygen that had the double bond only needs 4 dots, and the other 2 each need 6. So that's a total of 16. And so when we go over here, the oxygen that has the double bond is only going to get 2 dots, or excuse me, 2 sets of dots, whereas the other oxygens are going to get 3 sets. And then, there we go. And then you have to put the -2. So go to this one. The one going down only needs the 2 sets. The other ones need the 3 sets with a total of 6. And this needs a -2. And I go to this picture. This one, you're going to be seeing dots in your sleep, aren't you, when you're drawing these? Like dots everywhere sometimes. And then we need the bracket. Ooh, I was running out of room. These 3 structures are called Lewis structures. And this happens not just with ions, it can happen with molecules. Like you've heard of the molecule ozone. Let's go through the process with ozone. So ozone, let's see, we have 3 oxygens. So 3 times 6 is 18 electrons available. So it's actually a little bit of a bent molecule. I happen to know that, so I'm just going to draw it that way. If you drew it straight across, that's fine. But I used 4, so I'm going to subtract out 4, and that gives me 14. Now, I'm going to need a double. How do I know that? Because I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I need 16, and I've only got 14. So I got to put a double bond in. But the question is, well, which one gets the double? The one on the left or the one on the right? Remember, if they're equal, they're like 2 equal structures. That means that it could be either one, and you need to draw them both because they are resonance structures. So I'm going to make room here for both. And I've got one of them that's going to have the double to the oxygen on the left. And the other one's going to have the double on the oxygen to the right. I now used 2 more, so I have 12 electrons to distribute. Remember, the oxygen with the single bond right here needs 6. 1, 2, 3, 4, 5, 6. The oxygen with the double bond only needs 4. 1, 2, 3, 4. The oxygen in the middle already has 3 bonds. It only needs 2 more. So if you count, I just used 12 dots. So I go to the structure over here. The single oxygen needs 6 dots. The oxygen with the double bond needs 4 dots. And the one in the middle only needs 2. I used 12 dots. These are resonance structures. And I don't need like brackets with charges because it's a molecule. Okay. So there are many different, you know, ions and molecules that do this. Okay. And you might come across them, especially when you're taking like something like AP Bio or college biology. There's a number of molecules that have resonance structures that do this, that are part of our biochemical makeup. So remember, anytime you're trying to work out a Lewis structure, first figure out how many valence electrons you have to use. Then draw the skeletal structure, subtract out the electrons that you used drawing the skeletal structure, and then examine your structure and see how many more you need and compare that to how many you still have. If there's a discrepancy, you got to go back and work on making like a double or a triple bond, see where it's possible, see how many electrons you still need, distribute those dots, and then kind of examine what you end up with and make sure that all of the elements have a total of 8 electrons around them. Dots count as 1, but the dashes count as 2. And then if there were any extra electrons, like with those ions, make sure that you put the brackets and the charge. Okay. So good luck. Hopefully that helped. And good luck with drawing structures. See me if you have any questions.